Okay.
So let me introduce Dr. Shahnawaz. He's our research professor at Arizona State University, Atmospheric Water Harvesting team. So we want to start another session, highlighted talk. He will be the moderator here, and Dr. Shahnawaz, the mic is yours right now.
Yeah, first, I'd like to say that Amin has a lot of energy. He could have easily have done the second session, but he's just giving me an opportunity to moderate this session. So thank you, Amin, for this opportunity.
Most welcome.
And this afternoon, I think this session, we have three very interesting presentation. And I think this is a very interesting talk from from Delia. And this is about the new bottling plant in the project in southern Peru. It's called Aquapurse. Brand offers atmospheric water harvesting system capable of generating large amount of water. And this project aims to produce bottled water using and focusing on region high temperature and high humidity. Ms. Brito is a marketing and a sales expert over more than 10 years of experience in LVMH Group and other fashion companies. In 2023, she shifted her focus from an eco-friendly industry and joined the Purse EcoTech to lead their expansion in Europe. Based on Malaga, Spain, Purse EcoTech developed sustainable solution, including adiabatic refrigeration system for the atmospheric water generator system under the Purse brand. And with that, we would like to welcome you.
Thank you very much, first of all, for the opportunity. And yes, I'm more than honored, to be sharing this presentation with you all, because as you've seen, I am no professor. I am basically a person who is absolutely passionate about atmospheric water harvesting, generation, however we want to call it. And my job is basically to communicate on all the benefits of this technology to everyone, because pretty much we are having customers, I suppose Ms. Katani at CEAS has at the moment. So yeah, basically my presentation was basically, first of all, present, how AWG is making a difference nowadays everywhere, because as you know, and AWG is not only a solution as we had known in the previous, years, for, remote communities in third world countries, because the problem of drought, water scarcity, and, this sensitivity towards water quality is pretty much something very present nowadays, also in many countries in the Eurozone, in the States, let's say first world countries. So, and then also, obviously, how AWG can be brought, obviously, to the next level. So it's not only, how to harvest water, to provide water to the people in need, but also, to do a business out of it, which is, I think, is the ultimate, sophistication of the whole technology. So yes, as many of my predecessors have mentioned before, water stress is not only a problem as we knew before in like rural or remote areas in Africa, in Southern Asia or Latin America. It is pretty much nowadays, even at home here in Spain, as you can see in some of the charts, it is pretty much a problem that we are facing in Spain, Italy, all the northern countries of Africa. And although this chart is from 2050, I'm sure it is totally applicable nowadays. And yes, it is also a political problem, which we're starting to see in many conflicts. And also the other side of the coin is that not only it is a problem of water scarcity, there is more and more a growing sensitivity everywhere in the world towards water quality. PFAS, like nanoplastics, drugs present in the water that we drink from the tap also. So obviously, when you take all that into consideration, okay, atmospheric water generators can no longer be as they used to be, so that's why us at Aquapurse, we decided, to shift completely, the narrative and bring this these generators, you know, to the first world, you know, make them, you know, beautiful, make them accessible, make them, you know, something that can be working, you know, in any kitchen, in a counter, you know, on a counter top, you know, of anyone's kitchen, the first, second, third world, whenever, you know, all these machines, for instance, they can work in any home, in any kitchen, okay, in an office, in the waiting area of your dentist. And then we also have machines that are more powerful because they have a larger capacity. Now we're talking more about, you know, in the thousands of generation of liters per day that can be used, you know, in our country, for instance, you know, to filling external deposit tanks, you know, or reservoirs, to water the plants, to be a totally autonomous of water in your home, to fill in the swimming pool, you know. It's a totally different narrative that we are facing now. So yeah, let's say that from generators that are able to do under optimal conditions of 30 degrees, 80% humidity, 10 liters a day, 20, 50, 100, 1,000, okay? We're able also now to have, you know, also machines that can even go up to 10,000 liters a day. Okay, so now, so this is why we're no longer talking about small, you know, smaller amounts, but larger amounts that can be, you know, attractive, you know, for other kinds of customers. So having said that, okay, and bearing in mind that it is very important, you know, to know to what customer you're, you know, with which customer you're dealing with. How do they work? You know, how do you present this technology? First of all, it is a very simple, and I think Miss Katani explained it very well. Nowadays, generators, you know, are very, you know, very performant machines. And for instance, or generators, you know, they start, you know, producing water only with 150 watts per hour, you know. And even the most powerful one, the 10,000 liters per hour one, only consumes 125 kilowatts per hour, which, if you think about it, you know, and you're generating 10,000 liters a day, it is quite already, it's quite impressive. But I mean, one of the main things is that they are very, very simple in their functioning. You need a very powerful compressor, okay? You have performant filters, you know, on board, obviously air and water filters, okay? And in our case, in Aquapars, I think that one of the key things, you know, to make our generators so performant is not only obviously the, you know, the compressor, obviously, that has to be very performant, but also that has a very low consumption, okay? Another thing is the isolation of the system, which is also very, very important. And thirdly, but not, you know, least important, is the evaporator. Our evaporator is made of copper and with tiny plates. So obviously that also helps, you know, making it more performant, you know, and again, ensures a very low consumption. But again, as I said, a very simple system that can be understood by anyone. You have to make it very performant, you know, and also obviously low consumption is a key thing, especially because when you're talking also of customers in our countries, the necessity of being autonomous is also very key, because you have more and more people, you know, having solar panels in their houses, and they also want to be autonomous in the water, you know, consumption in their homes. So that's why, for instance, also our generators can also work with solar panels. Okay, so again, for this kind of customers, okay, it has to be very easy. It has to be, you know, with a plug and play system, no installation. When you think about, you know, generators, it has to be, you know, something super easy for everyone. Not only the, you know, the lady that buys the generator for her kitchen, for her family, but also, as we will see, the 10,000 liter one. You know, you only need a 40 feet, you know, container to transport it. And once you say, okay, I want it here, this is where I want to have my source of water, you just leave it there, plug it, and then you start generating water. So again, it has to be very simple. And this is how they are, okay? As I said before, they can all work with solar panels, okay? So as a way of being autonomous, it makes total sense that you're able also to connect them with your solar installation, okay? Low and easy maintenance. Okay, the only thing that you need is to change the filters, and that's we have measured that it should be done more or less in about a year, okay, depending on the consumption that you do, depending on the air quality that you have, but also how intense, you know, you make the generator work, okay, because it's not the same thing to have a machine, sorry, a generator that's going to be working in a secondary home than in your own home, okay? So that's why, you know, the intensity is very important. And very also key for generators, and this is something that Ms. Katani has also evoked. It's very important to know when and how, you know, can your generators do the most, okay? In our case, we have measured the capacity of our generators. Again, they can start generate water with 5 degrees Celsius and only 20% humidity. Okay, so it's quite low according to conditions. Okay, so these conditions are very low, but with these conditions, with these extreme conditions, so to say, we can already generate water. Okay, then obviously, the more performant you know your compressor is. So maybe, let's say, the bigger your generator is, the more water you will get, obviously. But we're able to do that also from that point. And of course, peak production at 30 degrees and 80% humidity, which we all agree it's the perfect you know, situation. But again, it is not a situation that you have everywhere. Okay, and this is very key to know. So this brings us to our case study this afternoon, which is, how to bring AWG to the next level. This is how to make a business out of it. And this is basically, how we were contacted by a company in the south of Peru. They contacted us because they had already had experiences with AWG in the past. They saw that we had large machines, okay, and they proposed us, okay, we want to start bottling atmospheric water, you know, do a 360 project, you know, bottling them in a very sustainable material, which in this case for them is aluminium PAT. And they said, okay, we set a target, okay, of 10 to 20 liters, 1,000 liters, sorry, per day. Okay, so with that information, okay, we had to work, you know, at Aguapars and see how we could work together to make this happen. Now, in the area, very important, thumbs up to the humidity, because it's true, it is an area with a high humidity level, you know, consistent from 72, 75% to 80%, you know, regularly throughout the year. But as we've seen before, the challenge came from the temperatures. And this is why this case study for us is very important, because once we know how to solve the temperature issue, we can bring this, this project to many places, for instance, in our own country, in Spain, where we have, I mean, don't think that Spain is always sunny. We have humidity, you know, it's always like in the Balearic Islands or in the Canary Islands. I mean, we have areas with high humidity, but also low temperatures, or let's say rather average temperatures. So that's why this study for us was very important. So we proposed to them, okay, to have 2 of these of our largest machines, which is the AP 10,000 model, which is able to produce each under optimum conditions, 10,000 liters a day. Okay, we would ship them, as I said, very easily with a 40 DV container. Okay, and these are the features of the plant. So very important for them, obviously, was the water generating power. In order to make their business scale. Okay, how much is it going to consume? In terms of electricity. To break this down and see if this is workable. From a business perspective. So for them, it was very positive to see that it only consumed 125 kilowatts per hour, because then that meant that with the price of the electricity in Peru, it made sense, to go ahead with the project. So then again came back, as I would say, the issue of the temperature. Okay, this is a graph where you can see how performant the AP 10,000 is according to temperature and humidity. Okay, so basically this would be the ideal situation. But where are we? Here. So we are in the line of the lines of the 70-80% humidity, but rather on the left because the temperatures are rather low. So our objective was to bring these results to the optimum one. So when we also started with the production that we would get, just by bringing the machines, not doing anything, yeah, I mean, we knew that there was going to be a challenge, and obviously here it is. Instead of having consistently 10,000 liters a day, let's say, per machine, we would only get, let's say, more or less like less than half the generation capacity. Okay, so this is why for us it was very important, to bring in a solution, to improve these temperatures and make the capacity grow. So what was the proposal? Okay. And also taking into account that for us to maintain a low consumption, of electricity was very key. We didn't want, to bring in any other element in the generator that would be costly in terms of electricity. So we thought of a very smart and very simple system, to bring up the inlet temperature air, temperature of the inlet air. Okay. With a very simple system, okay? Basically, by playing with the different channels, okay, of air that come in and go out. Why? Because we have measured the temperature of the air coming out of the generator, okay? And it's always consistently close to 50 degrees. 45, 50 degrees is more or less the average temperatures that we have. So if we could use this air, this hot air, to bring up the temperature of the inlet air, that could be a possibility. So this is basically what we thought. Okay, so this is how the outlet air duct would work. Okay, so basically you have the air coming out of the machine in high temperature. Okay, very important. It has to be isolated, to keep the heat inside. Okay, because this is the key element of the whole system. The key area where the inlet air is going to be heated. This is the interior air inlet. Okay, so this is where the cold air is coming in the generator. And we made it out of aluminum, okay, to absorb the heat from the outlet air, to make it work, it's its job, and heat this air, and have a really full-on, like heat exchanger. So this is how it would look like, okay, in terms of how the air circulation, okay. And this is how the whole system would look like. So you have on the one side the hot air coming out and heating, the channel of the fresh or cold inlet air that goes in the generator. So it's a very easy, very simple way of heating the air. And in terms of cost, it's also very I would say very economic, because we're talking about aluminum, we're talking about galvanized metal, with maybe glass wool, to do the isolation system. So again, trying to make it, cost effective, and obviously as performant as possible. So we finished the test, and actually temperatures rose by 20 degrees, which was very, very positive. We also thought about the possibility of modulating the heat exchange with the system of windows, because obviously you can have days, maybe, like extraordinary days with extraordinary temperatures, and you wouldn't want to overheat, the air, because then, I don't know if you saw before in the chart, but when you reach certain temperatures, like around 40 degrees, the capacity of generation goes slightly down. So if you want to make sure that we're keeping, the highest level of temperature and humidity to make the machine as performant as possible, we wouldn't want to overheat it. So that's why we thought also about a system of windows, to cool a bit, the heat exchange also. And we thought also that for very cold areas, okay? There is also a possibility of putting an electric, or gas heater inside the air inlet, okay, to even push further the temperatures, and also to have a control over that. So this is our project. I don't know if you have any questions. It was my pleasure to present it to you.
Yeah, very interesting talk. Really liked that engineering you guys did in bringing the air a little bit hotter using the exhaust air. Is there any question from anyone? Please raise your hand or just type your questions.
Okay, I'm reading one here. Installing a small, hold on. Installing a small size AWG in indoor environment, such as a house or an office, can cause indoor discomfort with people due to excessive dehumidification? No. Actually, okay, I always say that these machines, okay, these generators, they are opportunistic. I don't know if you say that in English. I'm sorry, I'm a bit tired. It's a bit late here in Spain, but we call them opportunistic because basically they take the atmospheric humidity to provide, to bring, to produce water, but then the outlet air, although it's going to be hot, is not that dehumidified. Having said that, obviously, we never recommend to have, any of the generators, even the smaller or even the biggest one, in a very enclosed area, because we need, air circulation, okay? And that's why this system that, of heat in the air, it's open. So it's not an enclosed, it's not a closed system. It's open, because we want to have always fresh, air, fresh by mean clean, air coming in. So so they're opportunistic, okay? You wouldn't feel a dehumidification, but again, you don't want to kill the generator, okay? I always say the generator needs electricity, even if it's small quantity, even if they're very performant, and low consumption, but they also need humidity. So yeah, so that's it.
There's one more question.
There is also an issue related to biological pollution, which must be addressed. Biological pollution. Do you mean in the incoming air?
Or the water that is being generated from the incoming air?
From the incoming air, okay. For that, but I think, I'm not talking solely about Aguapars, but I believe every other manufacturer of water generators work with certain air filters. I can only talk about ours because these are the ones that I know, and ours, they are double, okay? We have a HEPA, so HEPA filter, and a active carbon one, okay? So basically, and they're really filtered to a very, very small, level. So yeah, no pollution can get in the compressor, so to say. And I say that it doesn't really matter where you put the generator. There's not going to be a change in the taste of the water if you put it in, I don't know, center of Manhattan with all the car pollution and everything, or in the middle of the countryside. The water is going to be always the same. It's always going to taste the same. So no, there's no contamination in that sense.
Okay. What about the water that you produce? Do you disinfect that water? Is there any ultraviolet disinfection?
Yes, of course. Okay. Maybe I went a bit quick in that area because I assume that, we have some people around here that also deal with generators. Okay, I'm going to go back to that idea very, very quickly. So how do they work? Okay, you have basically an air filter, you have a ventilator that's going to absorb, the air. Okay, so that's why it's very important that the air coming in has enough, humidity and certain temperature, because then it goes straight to the compressor, okay, to generate the water, okay. Then the water goes into a tank, okay. We have also a certain heat exchange system, okay, so that the water always stays fresh. And also we work with UV lamps, okay. which is very important to always keep the water in the tank, bacteria free. Another very important thing about generators is that if you think, if you take any example, I'm going to take the small generator. Our smallest generator can generate 10 liters of water per day, but the tank is only a 6 liters one. Why? And everyone's asking me, why, if you're able to produce 10 liters, doesn't your machine have a 10-liter tank? Because we want the generator to be generating all the time and have the water always freshly generated. So, and that's why also people ask, yeah, but do I have to have it plugged all the time? Yes, you should have it plugged all the time, mainly because obviously you want to have the UV lamp on all the time, so there's no bacteria in the tank, but also because whenever you take out water, you want the generator to start again generating water, so that you always have the freshest water generated, And what I'm saying now is applicable to any generator, to the 10, to the 100, to the 1,000 liters a day, even to the 10,000 liters a day. They all work the same. It's the same principle, only bigger.
I think that there were like a few questions about that on the water quality side. I think you have addressed all that. And then you nicely explain like how the system works. That is pretty good. So is there a few more questions maybe?
Hold on there. Okay. When the temperature of air rises, the duct heat exchanger, what happens to the relative humidity of the air? Don't they get lowered? As we know, temperature increases and relative heat decreases. No, it doesn't. I mean, we still have a humidity in the inlet air, and yeah, it's still very performant. What's your opinion if we used gel that cooled a 10 centimeter a gel? Oh, sorry, Mohammed Gaber. Maybe you can send me that question to my email, because I don't know what you mean by gel. I mean, we work with compressors, no desiccants, just a performant compressor. Does the inlet of the generator need to be kept a certain distance? Sorry, does the inlet of the generator need to be kept a certain distance?
Yes.
Yeah, but that's why we work with different channels, okay? With different channels, so that the air and isolating systems, okay, in every channel, so that they don't mix up. Let's maybe, I don't know, you have a big channel, okay, that has the hot air coming out of the machine, and inside, okay, you have the other one, okay, of the inlet, the cold one. So this one is going to hit this one, basically. I don't know if I'm making myself more clear like that. So yeah, they don't mix themselves. They're different channels, one inside the other, yeah.
Do you get any type of condensation happening inside as you heat up the air?
Sorry, is there?
Do you get any condensation happening in the duct, like as you now mixing the hot in two different channels, the incoming?
I haven't seen that actually. If there has been any, I would have to check with my technician. But to my knowledge, there was absolutely no issue about the condensation. But especially because of that, because they were, we try to model it so that the system worked, perfectly. We didn't try, to raise, a lot the temperature, so that then we would get condensation or any other issue, to make it, really smooth. So that's why it's important that you also can work with windows, a way of, not to make it very so strong that maybe exactly you get maybe condensation. It's a way of doing it also, with these windows. Atmospheric water harvesting.
I'm so sorry to interrupt you, because
yes,
we are
sorry,
running out of the time.
Yes,
we can take one question from Dr. Lucia, and we will go ahead for the next session.
Yes.
Thank you so much. I beg your pardon, but there is a thing that, in my opinion, must be explained well. If I've got external air at low temperature, with its humidity and I heat up it, the water content in air remains the same. So we obtain that the temperature is higher, but the relative humidity decreases. So in order to harvest water, this is not a very useful thing to do, because the sensible heat is increased, and in order to harvest water, we must dispose such a sensible heating, and thus we will consume more energy in order to harvest such a water. Thus, to heat up the external air is not useful in order to make water condensation with such a machine, because we are not enhancing the water content. We are only enhancing the temperature, and we are lowering the relative humidity. This is the physical process. Okay.
No, but that's the thing. We don't really heat the air with any heater. That's the thing. We don't bring any heater.
Even,
I mean, we have thought about it, to be honest, for even extremer conditions. Like I have been contacted by someone in the south of Chile, close to Antarctica. And so, yeah, we're thinking about, how to even further improve this system, for even more, because here we're talking about temperatures, 15 degrees, 20 degrees. Okay. I'm talking about, people with 5 degrees or even less. So yeah.
Okay, but you must add water, because you have got some air, which is, for example, 5 degrees centigrade with a 10% of humidity. You have got 5 grams of water for cubic meter. If you enhance such a temperature to 15 degrees centigrade, you have 5 grams of water per cubic meter, not more. But you have the temperature at 15 degrees centigrade.
No,
so
but
if you want to enhance the water, the water harvesting, you have to capture such water in another way, or to enhance the water content. So you must enhance the temperature and the relative humidity by means of some adding, by means, for example, sorption and desorption materials. Okay, basta. Okay,
no,
I stopped myself.
Sorry, Lucia. I'm not talking about a place with very low humidity. I mean, here what we're solving is a much wider problem, because I think worldwide there are more places in the world with high humidity and low temperatures than, unfortunately, and there are, because as I was telling you, we've been contacted by someone in the south of Chile, which have low humidity and low temperatures. We have estimated that below 20% humidity, it is almost impossible, to condensate water. Okay, at least with our current compressors, for us it is impossible at the moment. Okay, so we have always to work above 20%. Even I would say 25%, okay, 20-25% humidity level, and then work with temperatures, because that's when you can respond to more customers actually in need, because these are the people that are contacting us, as they might be also contacting you in SCAS. So yeah. So no. We're talking only about temperature, not humidity. Humidity, at least 20%. We have to work with a minimum of 20-25, and still this is very, very low, very low. Here we're talking about a place with a lovely 70-80% humidity level, but low temperatures. So yeah, the issue is another.
Perfect. Dr. Shahnawaz, Dr. Ahmad Jamil is right now ready for his presentation. You can introduce him. Thank you, Ms. Dilia.
Thank you for the great presentation. So, Dr. Muhammad Jamil, are you there? Okay.
Hello.
Great.
Yes, you can hear me.
Okay. Yeah, I could hear you. So I think I gave a short introduction on you, but I will make it again a shorter one. So I think today you're going to talk about the solar to water, very exciting technology. I think it got a lot of UK's coverage on this system. So you'll be talking about that one. In terms of your introduction, I think you're the CTO for the EcoTechX in Newcastle, UK. You hold a PhD degree in mechanical engineering from Northern University, and your research is focused mostly on water, energy, refrigeration, and air conditioning. You have more than 40 publications, and we're very much excited to hear more about your solar to water system. Thank you.
Oh, thank you very much. Thank you. And thank you. Last time when you called, I was actually traveling, so I had to stop on the site because I was expecting it to happen at 6:25. So, can you hear me and see my screen?
Yeah, we could hear you well, and we could also
Oh,
see your
thank you.
screen. Yeah.
Oh, thank you very much. So basically, we are working on this hybrid solar to water system, and today I will be presenting related to some material and process science developments that we have been doing since the last 1.5 year, particularly from the technology side. I am Mohammed Ahmad. I am working as a CTO in EcoTechX. So let's start with the SDGs that are very common in our talks these days. But if we look at all the 17 goals and 169 targets, we can summarize that three of them are directly or indirectly related to all of them. And the top of the line is the clean water and sanitation, and affordable and clean energy, and climate action. And among these, particularly the water is again related to both of these because most of the things related to food, energy, climate action, they are directly linked with the water, and of course, water is one of the basic necessity that and one of the formidable challenges that people are struggling to address. And there are different techniques for desalination and water conservation. But this air water generation or air water harvesting is one of the attractive techniques, particularly for the remote areas where we cannot deploy a big infrastructure. Rather, we have to go for the plug and play devices that can extract water from the outdoor air humidity. So just quickly looking at the current water statistics, we can see that there is 40% supply demand gap, and desalination is currently leading the market to address this with 80% contribution worldwide, particularly in Middle East where plenty of seawater is available and fresh water is the big challenge. And there are other, of course, strategies that are adopted to address these. But these technologies work perfectly fine when we are dealing with large levels, like on city levels, town halls. But when we go for this decentralized solutions, we come up with the two major techniques that are recommended based on their utility, like solar stills and air water generators. Again, with the solar still, the area of the area and time required to generate fresh water from a saline water using solar still is again pretty challenging. But these air water generators are active devices compared to the solar still, which are passive devices. So that's why we can go with that as a solution for difficult situations. So primarily, these air water generation systems are desiccant based active cooling technologies or fog harvestings. And pretty much of the research from the material side is done on this desiccant side because this has relatively low energy consumption compared to those the other refrigerant based systems, and particularly the stress coming from this chemical based refrigerant usage as per Montreal protocol is also one of the challenge that is stressing these systems to further to at least go for the environment friendly refrigerants or minimize the use of these refrigerants. So we are working on this desiccant side technologies, and it's not new. Of course, it's a very old technology, and people are working on this side, and hundreds of patents are already available. So I would like to share that what we identified while working on these technologies, that there are various characteristics of these adsorption materials that are being targeted from the material viewpoint, like adsorption enthalpy, pore volume, crystal size, crystal density. But among these, the most challenging part is related to this adsorption enthalpy and equilibrium uptake. Because when we are designing a system based on the adsorption technique or adsorption material, we have to look for that how quickly it can adsorb and desorb, and secondly, how high water uptake we can achieve in the compact area, because we cannot go for a very large area getting for a small amount of water. So this was from the material side. But when we look at the system requirements, For air water generation system, of course, it should be low energy. It should have high water uptake so that we can fit the system in the compact place, and it should have a cyclic stability so that we can define a reasonable life of the system, and of course the fast capture or release of the water that we are doing. So typical desiccant based systems were working. If we simply go for solar based systems, that the night time they undergo the absorption process, and during the daytime when the plenty of heat is available, either it's coming from the solar or some waste heat, then they undergo this desorption process. So the two major limitations with these systems were material and heat transfer mechanism for regeneration, and the passive operation, because we have to wait for the day long for this process to undergo one adsorption and desorption cycles. So again, available materials, various in the market are available, but most commonly used is the silica gel, uh, which is abundantly available because of its cost and high durability. But other options are there, zeolite and MOFs, but MOFs are currently used on the lab scale only, because and for producing the MOFs on this commercial scale development system and then packing them up is quite challenging from availability viewpoint as well as from the cost viewpoint. So the conventionally the silica gel is used in the form of beads, which is basically either used in on or coated desiccant base wheels, or it is packed in the heat exchangers in the form of beads. So we are targeting this particular area where the heat transfer was the major problem with the system performance. For example, when we pack these silica gel beads in the heat exchangers, the contact area is very small because these beads are in the spherical shape and they have very small contact area with the heat exchanger fins, from where they can get the heat transfer and they can regenerate them for the next cycle. So this was causing this poor heat transfer and high mass to area ratio, because we have to pack a large amount of silica gel to get the required water capacity. In addition to that, as we can see on the heat transfer resistance network, that around 6 different resistances were occurring by packing these silica gel beads in the heat exchangers. So because of this reason, around 25% of the overall heat transfer was occurring because of this contact resistance, because we were getting a very point contact type stuff in this arrangement. So then we come up with this idea of this coating of this silica gel on the heat exchanger, rather than going for the desiccant based dehumidifier, where we are using the desiccant wheels, where around 75% of the wheel is exposed to humidification and the remaining is exposed to dehumidification, and we have to apply high grade energy like electric heaters to get that done. So we come up with this idea of coating this silica gel powder on using different kind of binders. So this was the first point where we started our study from the material viewpoint, that we tried 7 different binders using that silica gel powder to coat them on the on our heat exchanger that we tested later on. So here are some of the material characteristics of the silica gel that we used, and the other characteristics of the binder that we found as the best binder in the current case for air water harvesting applications is the hydroxyl cellulose. So we did the coating using this binder on the heat exchanger, and did some of the SEMs where we can see that we have got a uniform distribution of this silica gel powder with the required binder and on the heat exchanger surface. And for the strengthening, we added a few bars, metallic bars in this coating process, so that the life and cyclic stability of the material will be higher, and we can use this system for relatively longer operations. So what happens when we shifted from silica gel beads to silica gel powder using the binder? As we can see that the first part demonstrates the silica gel granular beads that we normally see in the packed bed heat exchangers. The temperature difference is quite high in these in this case, as I mentioned earlier, because we are having only contact point contact and very low heat transfer. But when we we shifted this beads-based silica gel to this powder-based silica gel coating on the heat exchanger. The results were excellent in terms of the temperature difference was dropped, which means that the better heat transfer we were achieving at the heat transfer surface in the system. So the temperature differential reduced from 17 degree to 5 degree centigrade, which means that the system was attaining maximum heat from the heat exchanger to regenerate the silica gel. So resultantly, the overall heat transfer coefficient in the system boosted from 40 watt per meter Kelvin to around 120 watt per meter Kelvin with the coating, which means that either we can go for the small amount of heat input for the same amount of water production, or we can reduce the system size for the same amount of water production because of this high heat transfer, because we are cutting the area footprint of the overall system. Secondly, the cycling and the adsorption and desorption cycle time was reduced. As we can see, this dotted line shows the conventional packed heat exchanger where around 800 seconds were required to, and then 45 seconds again required to switching the cycle. But within the same time span, if we coat the heat exchanger with the high contact area of this powdered silica gel, we can get the same within the same time. We can get around 4 different cycles of this adsorption and desorption. So from this experiment, we concluded that this scheme that we introduced as a powdered silica gel coated on the heat exchanger reduced the switching time due to the less heat transfer resistance, and it offered low thermal and convective resistance, high heat transfer, and cycle operation is faster than the conventional packed bed heat exchangers. So similarly, we can reduce the unit size for the same capacity, or we can increase the performance within the system. Uh, and this was one of the biggest challenges for us because we were deploying this system on the remote locations, and the area footprint was one of the challenge for them because we have to carry this system on the utility point. Similarly, in the second phase, we did try with different type of arrangements, like we using the waste heat for regeneration by flowing the steam through the heat exchanger. But we tested another arrangement of this microwave based regeneration of the silica gel. The main idea was because these microwave based regeneration directly hit the water molecules inside the silica gel, because silica gel is not prone to these microwave waves, and it can directly hit the water, and then it can regenerate the silica gel easily. So when we tested this microwave based regeneration arrangement, we can see that this dotted line shows the omega inlet of the air that we were taking from the outside, and similarly omega outlet is showing that the omega was around close to 45 gram per kilogram from directly 10 gram per kilogram, which shows that it has a high efficiency in terms of regeneration for this particular application of this heat exchanger base silica gel arrangement that we were using in the system. So then we evaluated the COP of our system on different uh, uh, duration of microwave emissions, and we were able to achieve around 0.58 COP of the system, which is slightly higher than the conventional available arrangements where they normally report it close to 0.3 or 0.25 or 0.3. So as a result, when we plot this and few of these process and experiments were conducted at KAUST, and now the system stage development is done in UK, and we are testing the system in our lab scale, in our lab environment, and on the on-site scale in one of the places in Africa. We are planning to send the unit for actual testing. So here we can see that the current that microwave based arrangement that we proposed was able to achieve a COP of 0.87 compared to the available in the market of these different regeneration systems, like using electric heaters close to 0.58, which was one of the big catchy point for us to go for the commercialization of this system. And then we pitched this idea to Innovate UK, and we got 300K to actually commercialize this, to develop the commercial scale product, and then test it on site for the further verification of the results. So here is our unit for 15 to 20 liters per day water production operated on solar. Of course, we have the battery packs as well for the backup if we want to operate the same unit during the night time. And currently, from the status viewpoint of the technology at EcoTechX, we are developing the few systems based on the same principle that I explained earlier, and we are dispatching these systems to for the on-site testing. And one of the unit is going to Limpopo in South Africa, where they will be testing it under. We recently got the Innovate UK Sophie grant as well to send this system over there to test for a longer period of time to test the stability of the coated heat exchanger under different environmental conditions, because the climatic conditions are quite harsh over there. And similarly, the other components of the system and integration of the overall system. So here are a few of the awards for the technology that we presented at different stages, like at ASHRAE and similarly to IMECI and this SSCT Society, and this technology was covered by the PV magazine as well as one of the sustainable way of producing water using solar from the air. So overall catch of our technology and our idea that we have been working on and we patented is that if we can improve the heat transfer mechanism within these desiccant based systems, we can either compact the system or improve the overall performance of the system. I mean, we can go both ways to get maximum out of this air water generator systems. So thank you very much.
We have one more speaker to introduce, and so we'll just go from there. So our next speaker is Abdulbari Belouafi. Am I saying it right?
Okay. It's Abdulbari Belouafi.
Belouafi, okay. He's a mechanical engineer, an entrepreneur who studied at Aston University and University of Birmingham. He's a founder and CEO of NovNat Tech, a startup focused solving water scarcity issues throughout the innovative technology. And he has developed a new type of material for water harvesting he's going to talk about, and he's deeply involved in commercializing this technology. With that, I would like to welcome you, Mr. Bari, for your presentation.
Oh, thank you very much for the opportunity. It's been a quite a long yet insightful day. As Shahnazad said, my name is Abdulbari Belouafi. I'm co-founder and CEO of NovNat Tech, and today I'll be talking through a presentation titled "Breaking the Drought: The Role of Atmospheric Water Generation in Tackling Global Water Shortages." I appreciate, of course, that it's towards the end of the day, so I'll try to keep it as briefly as possible and stick to the time. Just to go over quickly what I'll talk through today, going through the role of atmospheric water generation, including current technologies and their challenges, speaking a little bit more about NovNat and what we are doing to tackle the global water shortage, and finally a call to action from the audience. It goes without saying that water is the source of life. Without water, life ends. And due to water scarcity, around $301 billion of business value is at risk, according to a report by the CDP. And this has caused water companies around the globe to commit to becoming water positive as part of their ESG plans, due to increasing water costs and stricter regulations coming into force. And this trend is continuing in the wrong direction. So we need to act, and we need to act now. As you can see from the image, it's projected that by 2050, major parts of the world will be classed as extremely high in terms of water stress. And this has, of course, resulted in a search for alternative sources and/or technologies, including, of course, atmospheric water generation. So where exactly does atmospheric water generation technology fit in? It is important to highlight that atmospheric water generation technology, or AWG technology, will not replace conventional water technologies such as desalination, rainwater harvesting, etc. Rather, it complements these methods through providing a decentralized and on-demand solution for water, particularly where other solutions are not feasible or sustainable. And by coupling AWG technology with renewable sources such as solar and wind, makes it a sustainable option for water generation with a minimal environmental impact. Now, of course, as with any technology, there are challenges and limitations. And in the case of current AWG technologies, They suffer from firstly being energy intensive. So for instance, looking at the two main AWG technologies being cooling condensation and desiccant-based AWG technologies. In the case of cooling condensation, lots of energy is required to cool large amounts of air, and the energy burden rapidly increases as humidity drops. On the other hand, desiccant-based AWG technology relies partly on the material performance, as most of the energy is spent on regenerating the desiccant. It is worth noting, however, here that unlike cooling condensation, changes in humidity have a significantly reduced effect on the overall energy consumption of the system in desiccant-based systems. Secondly, and another critical factor in the implementation of AWG technology to tackle the global water shortage is the scalability. In the case of cooling condensation systems, which rely solely on electricity, scaling to an industrial scale is simply not feasible. On the desiccant side, there is yet to be a system that has been successfully scaled to cater for industrial operations while maintaining reasonable energy demands. And thirdly, another critical factor is the geographical applicability. Relative humidity tends to be the metric used. However, this only gives part of the story. What is important to know is the amount of water in the air, or what's also known as the absolute humidity. In this regard, absorption is better. Tends to be better compared to cooling condensation in drier regions, typically in relative humidities less than 50%. While cooling condensation is best suited for areas where relative humidity and temperature are high, which tends to be, as you can see in the image, near coastal regions. So in the image on the left-hand side, you can see a plot of where cooling condensation technologies are better suited, absorption, and where both can be used. The issue here is that cooling condensation, like I said, is restricted to coastal regions. And the issue here is it's in direct competition with desalination, which is far superior in terms of energy efficiency and productivity. And finally, the cost, which is what every technology, no matter how good, boils down to, remains too high for large-scale operations. And these are only some of the challenges that we are taking on at NovNat. NovNat was founded in 2022 on the back of a breakthrough water MOF with the aim of developing pioneering industrial air-to-water systems and working towards UN's Sustainable Development Goals 6, 9, and 13. Our vision is to make water accessible anywhere and anytime, and we plan to do this through creating the world's most advanced industrial air-to-water systems powered by our revolutionary materials. And our core values revolve around honesty, reliability, accountability, collaboration, and innovation. To give you an idea about what we work with and what our technology is, we are developing metal organic framework-based water harvesting systems, what are also known as MOFs. As you've heard from previous speakers, MOFs are nanoporous materials that can be tuned to exclusively capture the desired gas. They are made up of metal atoms connected with organic linkers to create 3D porous structures and are ideal for gas separation and storage. How they work in our case is upon being exposed to the air, the MOF captures the humidity in the air. For every gram of MOF, in our case, up to 0.6 grams of water is captured, a record-breaking amount. And to extract the captured vapor, heat, of course, needs to be applied to the material. In our case, we can do this as low as 50 degrees Celsius. And obviously, the MOF is now fully regenerated and a new cycle can begin. The ultimate product that we plan to develop at NovNat Tech is the 10,000 litre plus litre per day system. We have gone from proof of concept to a process development unit in under 18 months and plan to develop a small-scale pilot that will be completed early next year. And the ultimate goal, like I said, is to develop a full-scale 10,000 litre plus per day system in early to mid 2026, which is capable of utilizing low-grade waste heat. And this is to be piloted in data centers, which suffer from huge water losses due to their cooling needs. Now, in terms of obviously looking at the competitive landscape and comparing NovNat's systems to other systems in the market, NovNat systems are scalable to industrial scale. They are functional anywhere and anytime. They can be assembled using standard readily available and already mass-produced components, bringing their costs significantly down. Similarly, with the materials, we ensure that all our MOFs are made from abundantly available raw materials. And as I mentioned earlier, our systems can utilize low-grade waste heat as low as 50 degrees Celsius, making us one of the only systems in the world capable of achieving this. We take pride in being a company that offers a complete solution, starting from adsorbent structure selection and tuning. We have created 4 novel and unique MOFs named NOV 1, 2, 3, and 4 for water applications. We also go on to the next step, which is binder selection, and ensuring that not only we maintain the performance of the MOF, but also choose binders that enhance the MOF's performance across certain relative humidities. We have also developed our own coating methods, and in terms of the systems, utilize multi-objective tools to optimize the parameters of the systems. And of course, going to the final steps, which is the system building. And we are currently at TRL 5, 6. We have a small scale prototype currently producing around 15 liters per day of water. And the next step, as I said, is to go to a 500 liter per day system to be piloted in a data center. Now, of course, the material performance is a critical part of the system. In our case, our materials display the lowest heat of adsorption ever recorded compared to other known MOFs such as MOF 303, aluminium fumarate, and silica gel and zeolites. As you can see here, the theoretical minimum is at 44 kilojoules per mole, which is the latent heat of vaporization of water. And we have come the closest so far to the theoretical minimum with NOV 1 at only 45 kilojoules per mole. Also, of course, the material alone does not tell the whole story, as it must be integrated in a way that utilizes its superior performance. So on a system level, you can see a comparison here between NovNat's adsorbents with other systems based on cooling condensation, the MOF 303 zeolites. And you can see that NovNat systems are the most energy efficient across different climates. And our preliminary studies, we have calculated a levelized cost of water per liter for a 10,000 liter per day system at a fraction of a penny, and are functional even at 10% relative humidity. Another critical factor in terms of the material performance is, of course, the kinetics. As you can see here, the first graph shows the uptake kinetics at different relative humidities. So you can see at 60% relative humidity, the material captures up to 54% of its body weight in just 25 minutes, and dropping to just 40% relative humidity captures up to 52% of its body weight in just half an hour. This allows for efficient dynamic loading and unloading in several applications, including AWG. The second graph also illustrates rapid cyclic time. The absorption was done at 25 degrees Celsius and 90% relative humidity, while desorption was done at 90 degrees Celsius dry heating. As you can see, the cycle time here achieved was 45 minutes, which is already extremely fast. However, we plan to make further enhancements to the kinetics through incorporating thermally conductive materials and bringing the cycle time to less than 10 minutes. In terms of capacity, another important factor, here we have a plot comparing NOV 1 with MOF 303 and silica gel in terms of both the volumetric and gravimetric capacity. So you can see here in terms of the volumetric capacity, which is the more critical of the two in our application, we achieve up to 3 times the volumetric capacity, hence achieving quite a compact system. And in terms of the stability, which is of course is important to allow for long-lasting systems. We have conducted rigorous testing in terms of the stability, and the material has shown no degradation whatsoever in the performance. In terms of the thermal stability, we've tested the materials both, the MOF alone up to 400 degrees Celsius, and as well as incorporating with the binder up to 200 degrees Celsius. What we can also do is as well what's known as inflection point manipulation. So through incorporating both hydrophilic and hydrophobic binders, we can manipulate the inflection point. As you can see here, shifting it to the right, up to 20% relative humidity, which makes the material more hydrophobic and has a lower energy cost. On the other hand, shifting it to the left to 10% relative humidity makes it more hydrophilic, and of course this comes with a higher energy cost. So this is tuned and adapted to achieve the best compromise based on the application. In terms of projects that we have completed or plan to do in the future, so we built, as you can see here, the AWG prototype funded by Innovate UK. We have also secured a further £1 million in funding, also from Innovate UK through Eurogia and Smart Advanced Manufacturing programs. One we've already started, and one we plan to start next year. And the aim of that is to pilot the system, a much larger system, in a geothermal power plant. And then finally, like I said, mentioned before, the 500 litre per day AWG pilot in a data center. Of course, this can only happen with a formidable team, which I have the privilege to be a part of. As I said, I'm co-founder and CEO. I'm also joined by Dr. Ibrahim Al-Baik, who's the co-founder and CTO and is the engineering lead, and Kamal Diab, who's the co-founder and chief scientific officer, who's in charge of the material development. I'd like to quote Henry Ford here. If everyone is moving forward together, then success takes care of itself. What's important, and this is something I think one of the previous speakers touched on, is the need for collaboration. And we are open to working together with, with HVAC companies, with people with expertise in data centers and geothermal power plants. We also want to raise awareness through publications, conferences, and networking events. And of course, to support our journey forward, are welcome to speak with, and connect with investors that are focused on climate change, and obviously even better if they have a water background. So in conclusion, we spoke about water scarcity and the role of AWG. I touched a bit about what NovNat is doing, and ended it with a call to action. It's important that we act now. And collaboration is one of our core values, and we are open to connecting. Thank you for your time. And these are our contact details if you'd like to get in touch. Thank you.
Dr. Shahnawaz, you are mute.
Oh, sorry. I'd like to thank you, Mr. Bari. Wonderful presentation, lots of exciting results. And I will just hand it to Amin for the next phase. But if there's any question, there's one quick question from someone. What would be the cost of your water, if we're not using the waste heat? If you could quickly answer that, and then we'll move to the next session. Yeah.
Yeah. So this will depend on the region where the system is located, but this can range from anywhere from £3 to up to £15 per meter cubed.
Okay. And
okay, thank you very much. We are running out of the time. Thank you, Dr. Barry. So right now, I would like to ask Mr. Gabe Rice. He's our project manager at Arizona State University, who will talk briefly about our center. And after that, we will announce the best presentation award.
Good evening. Good morning to those of you who are in the different time zones around the world. This is really a unique opportunity for us to come together and chat about atmospheric water harvesting, and this is really awesome. This is the second webinar we've done. We had one earlier in, I believe it was May, with the Asian continent and those countries, and it was in Chinese, and it was I understand it was a fantastic webinar. It was very well attended, just as this one is. We had very good participation, wonderful talks, wonderful discussions. And that's what we're about at the Global Center for Water Technology. And the Global Center of Water Technology is a pillar of the Arizona Water Innovation Initiative. And our vision is to create and demonstrate innovative technologies that will improve water quality and yield an additional 250,000 acre feet of sustainable water per year within a decade. And this will go across all economic industries, agriculture, and the municipalities here in Arizona specifically for this program. But this technology will be able to be disseminated throughout the world. There are many other countries that are facing droughts and water shortages, and to become water secure is a very, very important piece of providing well-being for your citizens and the population. So some of our goals are to organize and host experts on water technologies, and that's one of the reasons why we're doing these webinars now. And this is so that we can find out what everybody is doing, what's working, and then we can commercialize this technology and we can get it out there. Because if it just stays in the lab, it doesn't do anybody any good. Also, what we're trying to do is to leverage any other resources that we have that are in the same space and bring them all together so that we can address the market needs. And that's another really important reason why we're having these webinars and focusing on different areas of the world, because each area has a little bit different problem that needs to be addressed. But if we all put our heads together and talk about what we're doing, we can come up with solutions. A little bit more about the Global Center for Water Technology. We are going to host our second annual International Atmospheric Water Harvesting Summit. And this will occur on February 20th and 21st. Oops, I was supposed to put 2025 there, so it's next year. We had a very good turnout last year. Unfortunately, last year we kind of announced it a little bit late, and so that prohibited some of our international attendees from being able to come out to Arizona to make that trip. So get your visas now, get everything set, and please come out. It's wonderful weather at that time of the year, and we'd love to host you. While you're here, you can see the atmospheric water harvesting test bed that we have set up. We are currently expanding that. And so if you have any kind of technologies that you would like to share and have us test, if it works in Arizona, in our climate, it'll work anywhere. So that's one of the reasons why they're hosting these test beds. In the Global Center of Water Technology, we have funded 23 projects, and these projects are at various technology readiness levels, but they're on the low end. They're on the 1 to 3 scale. And recently, we had an opportunity to become a part of the NSF engines, and our engine is called the Southwest Sustainable Innovation Engine. And Paul Westerhoff is the director of the water portion. We're looking at to address the themes of water security, renewable energy, and carbon emissions. So energy, water, and carbon. And so those nexuses are where these come together. And the point of this, we call it SWISSY for short. The point of SWISSY is to leverage the expertise that's in Nevada and Utah and here in Arizona in this region to become a hub and to take some of those technologies that were in that lower TRL and to bring them to fruition, help them with startup companies, etc. So if anyone has an idea or wants to become involved, the companies need to be here in the Southwest. So you're more than welcome to either open a satellite company here or migrate. We're always open to welcoming new talent into this area as well. And so with that, I'm going to turn the time over for a moment for Jay Maliki from Do Water.
Hi, Jay. Can you hear us?
We'll give him another minute to respond.
Yes.
We are a little bit late, so he might have had to log off. But while we're waiting on that, one of the neat things about Do Water is they are helping with our water test beds. We're going to be working with them to test some of their equipment here in Arizona. And we're really excited about that partnership. And we're also really excited about the other opportunities that we're going to have working with Do Water in the near future. And
Perfect.
All right, so we'll move on. I know everybody's probably ready to go to bed. So without further ado, we have an award for outstanding presentation. And one of the reasons I wanted to introduce Jay is because they are sponsoring this award. And the award is in the amount of $1,000 US. And we're very grateful for Do Water for supporting that. And our winner for the most outstanding presentation, which was voted by everyone in this meeting, is Ahmad from Anura University. Ahmad, congratulations. Amin will be in touch with you, and we will work out how to get you that prize. And we are very thankful for everybody who attended. Thank you for your time, for all the effort that you put into preparing your presentations. We look forward to seeing you in February here in Tempe, Arizona. Thank you.
Sure. Okay, let me also pass the mic to Jay. Hello, Jay. We can see you.
Hi.
Yes, right now we can hear you.
Okay, I can hear you now. I'll make it quick. We'll make it quick. Congratulations. It's been a long day. Thank you. And we're honored to be part of this great initiative. Very impressive presenters, very fruitful day. So in brief, the Do Water Corporation is proud to be the leading provider of atmospheric water generators in the United States. Our equipment is in operation in every single state, with the exception of Alaska and Nevada for obvious reasons. While Do Water Corp is by far leading the industry on many fronts, including power consumption, space optimization, and the largest selection of residential, commercial, and industrial models available in the market today. We are here because we believe this is just the beginning and that there's still much, much more to be done. This is just the beginning for the atmospheric water harvesting industry. Improvements still need to be made on every front, including efficiency, power consumption, including space and weight optimization, and of course, including production cost. We need to push the boundaries and we need to reach new levels. We are here because we believe in you, in each one of you, the scientists that presented today, the researchers, the entrepreneurs, the academics, and the innovators. We believe that the collective work of all of us here will allow this goal to be achieved and for boundaries to be expanded and for innovation to reach unprecedented levels. Throughout such collaboration, atmospheric water harvesting can offer a real sustainable solution for water scarcity around the world. Congratulations to all the presenters who participated in today's event. We appreciate each one of you and believe each of your presentations was valuable and will contribute to the advancement of our industry. We specifically congratulate Professor Ahmad Hamid for being selected as the best presenter for today. Looking forward to support each one of you in any way we can and to see your inventions and innovations successful, and foremost for your efforts to translate into commercial and useful applications that would help humanity. Thank you again for the Arizona State University, the Global Center for Water Technology, and the International Atmospheric Water Harvesting Association for a great event today. See you all soon. Thank you.
Thank you very much, Jay. Thank you very much. Dr. Ahmad, do you want to give a very brief talk? Just in 1 minute.
It is my pleasure today to share this association in the presentation and listening to all the participants after about 38 years working in this area, and finally I can see the effort and winning the prize in this meeting. I'm very happy to be with you today, and I hope that our cooperation continue in the next years. Thank you very much.
Thank you, everyone. We are running out of the time. I really appreciate it. I hope we can see you in the nearest future in our summit in ASU in person. Thank you. I will upload this webinar at our website association. Thank you and have a great day. Thanks, Jay.
Thank
you very
Take
much.
care.
Hello, Dr.
Bye.
Shahnawaz. Hello. Bye-bye.
Thank you again.
Thank you all for your kind attention.